Hi, ja, wir sind zu zweit hier, Simone und ja, wir haben uns ein bisschen mit Containern beschäftigt und versuchen hier Überblick zu geben aus, ja, mit ein bisschen Embedded Blickwinkel. Und oh, I think we should switch to English. Sorry. It was announced as an English talk. Yeah, let's do it in English. So yeah, this is like it will be kind of basic lecture for containers, and we will try to give you an overview of Linux containers from an embedded point of view. And yeah, welcome, and let's start. So, in the very beginning, let's clarify why I said embedded containers. Can you next slide? So, I'm pretty sure you heard of containers already, and at least from my point of view, the goals why you use containers are very different in the different contexts. So if you think about AWS, the cloud world, there you typically containerize your software to make it scalable, to make it globally available. So you have one service you want to provide, and you want to abstract the hardware below. Next slide. If you now played with containers privately, maybe on your Raspberry Pi or on your server somewhere, then containers are very often used as a tool to minimize the setup effort. I mean, for sure, it's also security isolation and also hardware abstraction, but in this context, it's also about, okay, the admin of the server don't need to know the details how to set up the application, and therefore it's in a container, and you can just run the container and it just works. Okay, and in the embedded context, it's a bit different from my point of view, because it's not about running one service and make it globally available. It's about having one feature and add it to an existing embedded solution. So container is typically used as a kind of update bundle. And with a container, you want to provide a way to enable a fail-safe update, enable rollbacks, and also security isolation. But typically, it's not, the hardware below is not fully abstracted. You have you expose some aspects of the underlying hardware to the container, because else it would make no sense to run it on the embedded hardware. I mean, okay. So to summarize it. In the cloud world, it's usually about one service and you don't want to care about the hardware. Therefore, you use containers. In the embedded world, it's typically you care about the hardware. You know your system in detail and you want to add one specific feature in a kind of isolated and separately updatable way. Okay, thanks.
So now that Tom has given you an overview about what kind of different areas we want to distinguish in containers, I want to take a step back with you and go a little bit about the technical foundations of containers in general, regardless of now in the cloud, on an embedded device or wherever. So let's take a look. What is a container? So I would say there is no standard definition what a Linux container is, but let's assume we have one or more processes that run in an environment that we want to have isolated, and this environment comes with all the needed libs, dependencies, configuration, and so on, bundled into one image. So that is what we want to run, and what is this runtime now based on? To bring it to a maybe formula, it is namespaces and C groups, but you see here in the picture those already in the Linux kernel. We might have further security mechanisms additionally, like for example we could have an seccomp configuration to limit the system calls we allow, or maybe we are using SE Linux, but that I would all consider optional. The core pieces are namespaces and C groups as provided by the kernel, and then we have some container tooling that utilizes it to run the containers. So looking again at namespaces, namespaces are a Linux kernel feature. we are using to isolate resources from each other. So we can isolate the resources from the host system to the container, and how is this to be understood? So each process runs in a namespace anyway. Normally this is inherited by the parent, but with clone and its flags, we can also use, we can also create new namespaces, and then each namespace abstracts a certain system resource. What can we abstract? Yeah, well, I have here the list for you. It is C group. There we are abstracting C groups. I would skip that now because we will talk more about C groups in just a second. We can abstract IPC, so yeah, inter-process communication. So for example, the MQ in the ProcFS, sys5 IPC, and so on. Then we can abstract network, so network devices, the firewall rules, the routing table, and so on. So that the network devices and so on are not the same inside the container as outside. You have seen that before for sure already. That is of course realized with the network namespace. We can abstract mount points. Yeah, of course you don't see every file you have outside of your container, also inside your container. Well, that is exactly done with the mount point namespace. If you start your first process in the container, it usually has a PID that is well known to you, but it's also already taken outside of the container. For that, of course, there's also a namespace that abstracts this. Furthermore, we can have a different time, different UIDs and GIDs with the user namespace. And lastly, UTS is maybe a little bit misleadingly named, but this is for the host name and NIS domain name. So taking an example of the mount namespace, because it's so well to be depicted here, we would see the complete root namespace. And if we would now create, have a process that is running in this namespace and just create a child without any further flags, we would all see, for example, /etc again. But if we would use clone and create a new namespace and assign the mount point as wanted to this namespace, for example, the namespace 2 here, and then we would see, if we look at container etc, exactly this etc, but it would look to us not like /containers2 etc, but our view would be restricted to that box. And we could of course not see, I don't know, /var, for example. Okay, we have isolated resources like networking and so on and so forth with our namespaces already, but we have not declared yet what is our process allowed to do, or how can we limit the process to nonetheless harm us. So, I mean, funny people might implement funny containers. We don't want to give them all our CPU power for their funny stuff. So here C group comes in, and with C groups we can again limit processes further. So we here can limit then the resources from the system the process can use, and every process has its associated task struct in the kernel, and there the C groups of the thread are stored. And we can limit, for example, the CPU. So the minimum number of CPU shares is indeed, if the system is not busy, it can be more, but this is what shall be minimum available. And if you consider, okay, yeah, well, maybe I have, I don't know, 10% of available in my container, but nobody forbids me to set the rest to something else. So 90% might need to be available somewhere else as well, if you take it from that perspective. With CPU set, you can assign a specific core. I don't know, maybe it shall always run on CPU core 2 then the rest would be free as well. Freezer, there you can suspend and resume all processes in the C group. Yeah, with huge TLB you could limit the use of huge tables. I don't think it has too much of an impact in container runtime implementations, but I/O and memory, doing exactly what you think, like limiting the use of I/O devices and also the memory that a process can use are more relevant. Yeah, with perf event you can allow perf monitoring of processes in the same C group, so maybe you want to restrict that as well due to security considerations. Yeah, with PIDs you can limit the amount of processes to create it. That would defend, I think, already quite a bit against my fog bomb from before. And yeah, with RDMA you can limit the access to remote direct memory, maybe also a little bit more exotic and not always in scope. C group and namespaces are important for container runtimes, and you will see, I believe, no container runtime that makes no use of those at all. But there's more. I mentioned before we could have seccom, we could have SLinux or SMAC. For sure we will have capabilities, but that is a very quick overview, I would say, about the foundations. So now what do we take out of that? Well, the runtime should use all the namespaces provided as good as possible. Why I'm naming that? Yeah, we will see later that it was that they are not always equal. That we should use the we should have a good C group configuration, and if there is none applied by the user, there should be a good default. Yeah, we shall support for the limitation of capabilities, security mechanisms like seccom and so on. This is the foundations, we want them supported.
Good, then. Now you have an idea how this containers works, and let's take a look at how to use it. And I mean, to understand the beginning, we need to understand what's the difference of a container to a virtual machine. And I mean, yeah, virtual machines were available already before containers. And the big difference is that a virtual machine runs its own kernel. So if you run a virtual machine, you can choose a kernel version, you can even run different OSs. You have all the freedoms to run what you want on this virtual machine, but this comes with difficulties and restrictions, so if it's about hardware access. So as you may know, I mean, the operating system kernel is responsible for managing the hardware. And so if you want to have the hardware managed or accessible to your kernel in the virtual machine, then it cannot be owned by the kernel outside. So either you add virtualization or you have exclusive usage of your attached hardware for one VM and cannot share it between different VMs. And I mean, this virtualization always comes with a performance penalty, for sure. And yeah, with containers, you avoid this performance penalty, and you can easily share the resources with different containers running on your host machine or on your embedded device. Yeah, but you are bound to the kernel because there is just the kernel from the underlying operating system, which means so if you run a Ubuntu container on your Fedora notebook, then it will use the Fedora kernel and not the Ubuntu kernel. Good, and yeah, I mean, this also is clear that then it comes with the restrictions that if you're running a container on an x86 machine, it can only be a x86 container. It's, yeah, not 100% true, but in general. Yeah, so in general, your underlying OS needs to support the executing the binaries from your container, which limits you a bit to the used architecture. Next slide, please. Good. So we now know the namespaces on the very bottom, and I'm pretty sure you heard also names on top: Kubernetes, Docker, Podman, maybe also LXD. But there is more. So this Linux container stack is quite complex layered thing. And on the very high level, you have typically a kind of container management solution, which provides you a nice abstract interface. Then there is middleware and the pressure from the users and the big cloud hosters to have some standardization. And we will come to the standards later. So there are standards like the CRI or the OCI. And for most container solutions, you have a kind of high-level management component. Then you have some middleware, and then you have some very low-level component, which then does the interaction with the kernel and configures C groups and namespaces and all the things you need. Okay, next slide, please. Good. Then, okay. So the very high level, the management provides you complex high-level tasks and takes care of all these management activities, lifecycle management. What can I run? What are the images? What I can run? So this is all handled in this management level. And on the bottom, you have this the runtime, which then really uses syscalls to configure namespaces and does all this low-level stuff. And for all solutions, this is separated in two different software components, basically. Good. And I mean, especially in the context of an embedded system, where we have limited resources and want to make optimal use of the resources we have, the question is, from our point of view, so how much management do I really need? Because it's pretty sure if I have more comfort, more management, it's also cost performance. It's not for free. Good. Okay, and then it's a little bit out of I need to explain OCI because it's mentioned a lot, and I think many people use it, and not everyone know what it really is. I'm pretty sure. So the Open Container Initiative was founded by Docker. I mean, from a historical point of view, Docker, as the Docker company, brought this Linux container stuff to the mainstream. And I mean, under the pressure of the users, they agreed on standards because no big company is willing to invest lots of money into a proprietary solution which may disappear. And that's the reason why this OCI standard appeared. And the Open Container Initiative is now part of the Linux Foundation, and it provides open standards for application containers, and especially image specification and a runtime specification. And this was the two interface standard layers you saw in the stack before. Next slide, please. Good. Then for this software and for this management software and the goal, there are two dimensions for the implementation which are interesting from my point of view. I mean, the one thing is the architecture of the container stack at all, and there are daemon-based solutions and there are daemon-free solutions. I mean, it's pretty clear if you have a service running in the background, if you have a daemon, it makes things more easy, but it's also not for free. And if you have a high-privileged service, it has security implications in the end. So it's something you should consider when you choose your tooling. And then it's not all OCI and the Docker world. There's more, and there are different goals which are solved by this container tooling. From the OCI world, you typically have the application container, so you want to provide an environment to package one application, but there is also the world of system containers, which tend to be a lightweight VM. So in an application container, you typically start your application process, which makes you start more process, but it's for one application. And in a system container, you typically have an init manager, and then yeah, it feels like a full Linux machine. Okay, then let's take a look at these tools. So in the very beginning, it started with LXC, which was developed in parallel to this namespace and cgroups features and so on in the Linux kernel. LXC was in the beginning founded by IBM and later taken over by Canonical. And LXC, it's quite old. It's a daemon-free solution, and yeah, it tried to build lightweight VMs, so it's focusing on system containers. And yeah, it's a quite flexible tool, and you can use images, but you don't have to. You can also configure your LXC environments in a different way. Next slide, please. Good. Okay. Then Canonical tried to build on top of this and provide similar features as were provided in parallel by Docker and Co. So the OCI world, and they invented LXD, which is a daemon-based solution, but it's also focusing on system container. Yeah, but it has some nice features and drawbacks. So you can, with LXD, you can also manage your virtual machines, not just your containers, which can be a nice thing if you also want to have virtual machines. But it's not OCI compliant, so you cannot use this rich ecosystem of containers you have on Docker Hub and the other OCI container registries. And one quite big drawback from my point of view, especially for professional users embedded system, is that the backend of LXD is proprietary. So you have to use the Canonical backend, and this may not be. I think this is not acceptable for very many solutions. Okay, and then not too long ago, there were also political conflicts between LXD and the LXD community and Canonical. And Incus was forked. Incus is hosted under the Linux Containers project, but at the moment it's more or less LXD with less canonical dependencies, but not really. It's very close to LXD still. Good. Okay. Then in this OCI world, we have Docker, which founded the thing basically. And Docker is quite confusing thing because it has lots of stuff named the same way. There is a Docker Inc. company, and this Docker Inc. company provides a Docker daemon, which is taking care of the container lifecycle management, and there is a Docker command line client. So lots of different things with the same name. But it's the de facto standard solution for OCI containers. And OCI containers are always application containers. And okay, one nice thing to mention is that Docker supports layered images, which means if your images typically use lots of file system layers, and if you change something, you only need to download the changed layers and the rest is stable. So it helps to keep your updates small, but it's also not for free, as always. Good. Then, with the success of Docker, Red Hat wanted to have its own similar thing and started to develop Podman. Basically, so Podman is developed by Red Hat. It's intended as a drop-in replacement for Docker. It's a daemon-free solution, so Red Hat tried to learn from the fails of Docker before, and especially Docker had in the beginning some cases where security flaws in the Docker daemon allowed attackers to break out of the containers and take over the whole system. And because of the security considerations, Podman was developed as a daemon-free solution. It's also an OCI implementation, so it's compatible to all these Docker containers and all this OCI ecosystem. say, claim at least to be security focused. And yeah, for OCI you have open backends. And if you run big installations, yeah, cluster support is also there for Docker and for Podman, and yeah, also for LXD. Good. Then one other tool where you may see some references on some older publications is CoreOS Rocket. It comes from the beginning of this OCI world, and yeah, was initially developed by CoreOS, which was taken over by Red Hat, and I mean, finally Rocket was ended and somehow partially merged into Podman, or at least ideas was taken over into Podman. So if you still use Rocket, maybe you should take a look at Podman. Good. Okay, and then not really topic for our talk. I explain you in a minute why. There are these application sandboxes, which also become popular, and where there were many publications, discussions, articles in the last years. And I mean, one of the more discussed ones is Snap. Again, a canonical development, which is only the client, open source. The backend is again proprietary. And I mean, in comparison to the application containers, these sandboxes are intended for, or at least from my point of view, are more intended for systems which have a user, so not really embedded systems, because these application sandboxes provide user-mediated access to the host. And I mean, you know this for sure from your smartphones, where you can say, okay, this application is allowed to use Bluetooth network, whatever, and it's the same for this application sandboxes. And yeah, Snap is now also promoted as IoT solution, but with a proprietary backend and quite slow startup, not really a good solution from my point of view. Good, then, yeah, the other, more well-known thing in this application sandbox area is Flatpak, which is a community project. And I mean, it's completely open source, it's an open backend. There are multiple registries out there, and you can host your own one. But unfortunately, it's only focusing on UI applications, so not really a thing for embedded. Okay, and then the last thing of this container management tools we want to talk about today is CRIO. CRIO is a quite new one. It comes from the Kubernetes world. It's one implementation of this new container runtime interface, which is not really a standard, but an API defined by Kubernetes. And from a feature set, it's quite cool, but it's only intended as one component in the Kubernetes stack. So if you don't use Kubernetes, CRIO is unfortunately not so interesting. Next slide. Oh, I forgot about containerd. Okay, containerd is basically the core of Docker. I mean, also Docker changed their legal stuff in the recent years, and there was also heavy discussions with the community, and many people were not too happy that Docker became more restrictive, and because of this forth and back, in the end Docker agreed with the community to open source their core, and this core is basically containerd, and containerd was handed over to this cloud native computing foundation as head organization for taking care of this open source project. And containerd implements large aspects of the Docker container lifecycle management. It includes the image handling, but it's bit incomplete. It excludes the network namespace solution. So if you want to use network namespaces and use only containerd, you bring your own solution for the network namespaces, and you also have no solutions for volumes, which may or may not be a nice feature depending on your needs. And I mean, containerd itself can also not build images, but that's not so important point, I think. Good. And containerd and Creo built on top of these OCI runtimes, which we will talk next about. But let's shortly summarize these container management tools. So we have this LXD world with LXD, and Incus, but these tools are focusing primarily on system containers. And since we have typically quite limited resources in the embedded context, it makes not too much sense to run a full virtual machine, even if it's a lightweight one, on an embedded device. So that's the reason why we don't further consider these tools. Then we have this application sandbox area, but also this is not too interesting for embedded. And so in the end, from our point of view, at least, most interesting for usage in the embedded world are these OCI containers. And there we have as active projects Docker, Podman, and containerd, which are also intended for standalone usage and are still active developed. Good, then for the runtimes, for the OCI runtime specification, there are basically two implementations. We have runc, which is comes from the Open Container Initiative. It's a reference implementation for the OCI runtime specification, and it's a quite low-level tool for then really starting a container, bring a container up. And I mean, these runtimes don't work with images. They work with so-called OCI bundles. And on this OCI bundle level, you have already this layered file systems and also things abstracted. You have one root file system and you have a config JSON, which basically tells, okay, these are the namespaces to set up. This is my security configuration, my SecCom configuration, and so on. And then this tool takes care of configuring the kernel and running the initial process defined in the config JSON. Good. And as with Podman, there is also the Red Hat implementation. And from a feature point of view, they both runc and trun implement the OCI runtime specification. So there is not too much difference. And I mean, trun is intended as drop-in replacement for runc, which it also fulfills quite well from my point of view. And trun is written in C instead of Go, which makes it much more lightweight than runc. Oh, okay. And also one old thing maybe you have heard from Let Me Containerify. This was a project by Google, and it was the initial runtime used in the Google Cloud. But unfortunately, it's also end of life, so there are just runc and trun, at least as far as I know. Okay, and also there, both are worth a second look, and the Google tool is end of life, so not interesting anymore, unfortunately.
Okay, so now that we've nailed it down, what are tools to take a further look at? What are tools that are not relevant either because they're end of life or because they serve use cases that we don't consider too relevant for the embedded world? We have evaluated our tools. So how is it done? We want them to meet high security requirements. This is, of course, a little bit of a fuzzy. Of course you want that, but what is it? Okay, we can just compare what they have. We want to have a fast startup time. We are in the automotive embedded world, and if you restart your car after a breakdown in the middle of the street, you want it to be fast. You don't want to sit now 1 minute booting your car. You want usually your memory is constrained and size constrained, and often you want a read-only root file system and an A/B update scheme. How have we done that now? We have used Nginx as an example container for performance measurements, and we just compared building and running each solution with it, and I will walk you through it so that you get a feeling on how it was done and what are our measurements. So considering runc, as mentioned, we will have a bundle. So the bundle is the root FS and the config JSON. The config JSON we can just generate with runc spec. And if you then take a look at your config JSON that you will get, you see that we will have the namespaces configured. We will have capabilities already configured. And the only thing that you might want to change first is the entry command, or the command at the very top that specifies which process shall be executed. But of course you could there then configure further security mechanisms, for example seccomp. Now you see here Docker export and Docker create. This is what we use to just use always the same Nginx container from the Docker registry. So we just created the root file system with the available one so that every solution uses the same root file system to keep the comparison fair. And as they're all using the OCI standard, I think that's good enough. Then you can create the bundle and have the created container. Then the setup will already be in place as per your config JSON. But if you then take a look on your running processes, you will see that not Nginx is already running, but a stub process that holds onto those namespaces and so on. Runc init will be running, and then to really start the container, this runc start, if you've done that, you will see Nginx is running. As mentioned before, the network handling and so on will not be done, so you might want to do then a little bit of IP commands, but that is also rather trivial. You should manage, and then you should be greeted by Nginx already. If you take a look in your browser or use curl or whatever, then it's there. You can then do whatever you want, and if you are finalized, you can just use runc kill. The namespaces and so on will be removed, and with runc delete, you will remove everything before and are back into your default situation. So what is good about runc? Well, it's the de facto standard implementation. It has a large user base. It's below Docker, so I mean, a large user base, you can argue, okay, then also more security issues are found and so on, more stability issues are found. It's unlikely to get unmaintained and so on. That's a factor. I have here noted that it fully supports cgroup v2. Why is this noted especially? Well, crun supported cgroup v2 ahead of runc. Runc now also supports it, but crun was quite faster. You have a rootless option and to also run it rootless, but what was also an interesting finding, they have security audits published in their Git repository. So they have external firms and consultants and so on that did the security audits. And if you take a look on the findings there, they were quite minimal. So it was audited to be quite okay from processes, standpoints, and so on. So I would consider that a good sign. So the contra is, well, it needs more resources than crun. We have heard that before. You will see in a moment our measurement. But first, we had the point, okay, crun is a drop-in replacement. And if you now just remove crun in this slide and place runc there, you will have the slide that we had before again. The only difference is here that no explicit stub process will be created by crun. It will just still be with the crun create process, but from a functional point of view, I don't see any further difference if you consider those steps and in this kind of layer of abstraction. Well, you can see here the pro and contra to be quite similar to runc. The only difference is, well, it has a smaller user base, that's just true. And the pro is, well, the inverse as before, it needs less resources than runc. So let's take a look at the resources in detail. So what we see here is, first of all, the installed size. There you can see that runc is, factor 4 to 5, just bigger when it's installed in the system. Then we see here the memory usage. The memory usage was measured when starting a container. There you can also see that, crun needed around 30% less than runc. And last of all, the time to start a container. The time is considered from starting the container until the Nginx process itself can start. So all the setup before. And also factor 3 again around here. crun performed better. Coming to the container management tools, the slide again very similar here with containerd. So with containerd you can have a multiple command line clients for, but CTR comes with containerd directly if you install it, but there are also other interesting clients like nerdctl. I think you can see the steps are again very similar, so use and feel very same. What is good about containerd, it adds the management of the complete life cycle. That is something that it really enriches runc and crun with, because they don't have it. You have an API that you can use to integrate it further to tools that is then, for example, used, of course, by Docker to include it for them. You can, we had before the point that it's not possible to build, but there are command line clients like nerdctl that support that. And what I think is interesting, that it supports also encrypted images and containers, signing and verifying. You add something, you pay something, so you will need more resources than just using a runtime. It is per se not designed for direct use. So you might need further integration into your own tool, then it's fine. But if you want to use it directly, you might have some hurdles. And again, still no built-in networking or storage solution out of the box. So let's come to the last two ones. Here the picture gets a little bit smaller. With Docker we can just use docker pull, run and kill. So I guess you all know those steps. Let me just do a quick pro and con here as well. It's the de facto standard implementation. Again, more users, more tests, hopefully more bug reports and so on. You have the full feature set now available. There's nothing missing. You have your registry, you can build. You have the complete ecosystem now. There's nothing standard that you would be leaving out. You have the complete ecosystem, but do you really need it for an embedded system? That's a clear no from my point of view. So if you have now many features that you don't really need, but that are running maybe, that are costing resources, and that also more code, more issues, more security issues. I don't want to have any feature that I don't want running, so that's a clear contra. For Podman, the picture is the same. You can just now replace Podman with Docker, and you have the same picture as before. What is good? Well, it's demandless, so we have no resource consumption in the background. We have a faster startup. We have, again, the full feature set. Not so good. Smaller user base. And as with Docker, you might not need many things. Let's do a quick comparison on the value here as well. So you need to understand that those values are to be taken with a grain of salt. So you see containerd, the installation size, to be bigger than dockerd, but as mentioned before, containerd is part of Docker, so you need to add those numbers. It comes on top. And so you would have double the size for Docker if you consider both it's together as needed for running. So for the startup, containerd was still the fastest, but it's those seconds are, and then additionally the runtime itself needs to start again, needs to be considered, but no surprising values. We said before, Docker is the slowest, Docker is the biggest. You see the values. Containerd was fastest, then comes Podman, then comes Docker. That's the point. What now to choose? Which runtime is the best for embedded? Well, run C and C run are a little bit too low level for direct usage, but one of those we will need. From our point of view, there is no real difference in feature set. C-Run doesn't need to comply to the latest OCI standard. It fully implements it, but it can implement something else well on top. And normally, those features are interesting. And as it has the better performance data, also, we would just prefer C-Run. Just blame performance reasons here. A little bit harder is the decision which container management tool is now best for embedded. Here I would say that there is no general recommendation possible because it really considers how large scale is your embedded project, what is the ecosystem around it. Do you have maybe some vendor backend already for over-the-air updates and so on, or how is this looking? If you want to integrate into an existing ecosystem, then I would build on top of Containerd. If you are more in the, okay, I'll try it out once, I have only a few devices, I cannot invest so much effort also, because maybe I'm only 3 people for 3 months and so on. Yeah, then we would use either Docker or Podman. If everybody is familiar with Docker and you need high compatibility, you would most likely use Docker. Otherwise, if you have maybe a little bit more time, resources are more critical and so on, then we would recommend Podman. There is no general recommendation as impossible, but I would say Containerd if you need to integrate into further tooling, and else Docker or Podman. Good. That sums it up already from our side.
Yeah, thank you, Simone and Tom, and sorry to the audience for mixing up languages during the introduction. Of course, we are curious what kind of questions you come up with, so let's see.
Hi, thank you for your talk. One thing I missed in your evaluation is your, which you mentioned earlier, was your A/B setup. How are you doing that with these tools? Can you talk a bit about that?
Yeah, it's missing because we run a little bit out of time. So we don't have. I mean, we have done this research. We have not fully completed it. We don't have a recommendation for our automotive embedded Linux what to use, and yeah, we have experimented with Docker and Podman, and you can configure both in a way that you can have a read-only root file system, but Docker is a little bit more easy to configure. Podman is a little bit more easy to configure. Docker is a little bit more tricky to have it running on with a read-only root file system. And I mean, especially for the image management and the update solution, yeah, I'm not sure if you can find a generic answer without a specific without the context of a specific project, because I mean, especially in automotive, you typically have lots of requirements from the OEM, how this update looks like. You have existing backends. You have some middleware like adaptive AUTOSAR. So it's possible. Yeah, we have POCs, but not a solution which is polished enough to show it somewhere.
Thank you.
Okay, thank you for this. Okay, next question.
Thank you. In embedded systems, we often have interesting I/O devices or I/O interfaces. Cars, for example, you have the CAN bus and these kind of things. What are the standards that currently exist or that you would like to have in order to share access to embedded external devices from the containers?
I'm not sure if I got the question fully.
Like the devices that are around the computers that the containers might have need to have access to. Usually all these stacks here are only for internet applications that don't really support I/O devices. So what is the story for an embedded platform?
Okay, I mean, this is also for the automotive world at the moment quite specific. I mean, we have in our current projects, we have two kind of containers in use. We have, on the one hand, IoT containers, which are not from the OEMs, but from Microsoft and so on, which more or less just collect telemetry data and send it back to some cloud provider backend, which is then provide some evaluations to the OEMs. And we really have the containers for system functions. And these are then, in our case, typically adaptive AUTOSAR applications. And there, we have we share the base to reduce the disk size. We have bind-mounted partitions with Unix sockets to allow the communication between the applications. So there is not so much really I/O used in our cases because, I mean, I/O like CAN or really GPIO pins are typically handled by the real-time OS, the classic AUTOSAR running in parallel, and then the communication between the POSIX world and the real-time world is done using shared memory or even network. But I mean, you can just bind mount your devices into your container and then make it available. It's working. And then this is also only provides the devices you want to give access to, and also with the seccomp and the Linux security modules, you can give a quite specific and restricted access to the system. But I mean, in the very beginning we had the difference, okay, containers don't have their own kernel. So if you provide access to hardware or kernel configuration to your application containers, then you always have the risk that one application may interfere with other applications. I mean, if they can configure the kernel, it impacts everyone in the system, not just this container. I hope it answered the questions a bit.
Okay, it seems like this question was sufficiently answered. Do we have any other questions left? Doesn't seem like it. So, I would like to say thanks a lot for your talk. It was quite interesting, quite a nice overview of the containerization landscape. And so I hope all of you enjoyed it as well. And for that, I would like to ask a very warm applause for Simone and Tom. Thank you.
Thanks.